To start, I add 2.42 grams of copper 2 sulfate pentahydrate to the flask, followed by 0.94 mils of water, a magnetic stir bar, and then 2.36 grams of pyridine. This gives a deep blue copper complex that will help oxidize benzoin into Benzil, my target product. Benzil can also be made by other oxidation methods, including nitric acid oxidation of benzoin. After heating the mixture to 100 degrees Celsius, I add 1 gram of benzoin. At this stage, the reaction is often described as a copper-mediated redox process. Benzoin coordinates to the copper complex and transfers an electron to copper 2, forming a benzoin radical, and copper 1. After proton loss and further redox steps, Benzil is formed. In other words, copper is acting as a catalyst that helps remove the equivalent of hydrogen from benzoin and convert it into a diketone product. Next, oxygen from the air reoxidizes copper 1 back to copper 2, regenerating the active catalyst so the cycle can continue. After about 2 hours of heating, the reaction mixture turns green. That color change usually reflects a mixture of copper species together with the yellow Benzil product, rather than a single isolated green compound. Once the reaction is complete, I isolate the crude product and wash it with 10% hydrochloric acid to remove copper residues. I then use ether to extract any additional crude product from the aqueous layer, which helps improve recovery. After these steps, I attain about 60% yield of Benzil. I confirm the product using proton and carbon NMR. In the proton NMR, Benzil should consist only of aromatic protons, with no hydroxyl or benzylic proton signals from benzoin present. The carbon spectrum is even more diagnostic because Benzil shows a strong carbonyl resonance near 190 to 195 ppm, which is consistent with the diketone structure. Overall, this oxidation is useful because Benzil is an important intermediate in organic synthesis and a good example of how a simple oxidation can make a versatile product. Thanks for watching.